Hello, everybody. My name is Michael Hennerich. I'm software engineering manager at Analog Devices in Munich, and I'd like to welcome you to the presentation Kuiper Linux Simplify Hardware Prototyping with GNU Radio. So, software-defined or radio systems in general are much more than just the digitizer. There are lots of active mixed signal front-end components that require configuration, runtime, and control. So this includes programmable gain amplifiers, attenuators, synthesizers, PLL, up-down converters, RF switches for filter banks, tunable filters, beamformers, PA control, offset bias, or even like some system monitoring stuff. Some typical challenges. On the left, you see some pictures how a typical lab bench may look like. You see lots of interconnected evaluation prototype boards, lots of different power supplies, and typically no homogeneous way to control this mess. This has some implications, sometimes loss of RF performance, but more difficult is that this is very difficult to test in the field or bring to a customer. Also, it's a kind of a control nightmare because you often have like different vendors, evaluation, hardware, software systems, and sometimes there's no software at all, and there's no easy way to remote control this, and you cannot integrate that in the GNU Radio flow graph. So there are a number of possible solutions. One is to kind of do a custom PCB design with a system controller, some custom firmware, but that's typically high cost and high risk, and it typically comes second after the prototyping phase. So in this presentation, we want to use commercially off-the-shelf control hardware and open source software, in this case, Linux. So in the abstract, we said we would build an FMCW radar system. That's what we're doing now. FMCW stands for frequency modulated continuous wave. It's kind of different than from pulsed radar. In the figure below, you see a kind of a ramping waveform that ramps in frequency over time. And in red, it's the transmit waveform, and in green, the receive waveform. And there's a time delay, and that time delay manifests in a offset, frequency offset, that's called the beat frequency. So to the right, there's the radar equation, and you basically see that the distance to target is proportional to that beat frequency. Also, you see that the kind of the ramp rate as well as the bandwidth of the modulated signal is significant in the equation and defines the characteristic of this radio system or radar system. So, thanks to John Graft, he kind of helped me prototyping this, and also was so kind to actually build that up and take a video. We were gonna see that in a minute, but here it's kind of the top level overview. We have a digitizer. In this case, it's an add-on Bluetooth. It can be anything. It can be any URSRP or any other SDR, because we have pretty low bandwidth on that side. Then we have the RF front end that's kind of composed by a number of blocks. Most important is the frequency ramping synthesizer in here, the ADF4159 with an external VCO, some attenuators, splitters, mixers, filters, and also a power amplifier. That all is controlled by a single Raspberry Pi in kind of as a control bridge, and that Raspberry Pi connects to your PC running GNU Radio Companion over a network interface. So this is how the prototype looks like. In this case, we're using like an X microwave plate with an X microwave controller, and that controller has kind of two interfaces. One is a Raspberry Pi head with control signals for SPI, I2C, GPIOs, and the other one is a FMC connector, so you can also connect that to a FPGA carrier. That is our very simple Hello World FMCW flow graph. Again, I've split it into two portions. One is the digitizer with some source and sinks, And on the right side, we see the RF front-end control portion that we want to discuss a little bit more in this presentation. But now I think it's time for the demo, and I hope it's playing.
Right, so this is our setup with that radar that we just built. You can see the X microwave plate there connected to Pluto and connected to two X-band antennas. Actually an array of antennas, but we've only connected two of them, one for transmit and one for receive. And then on the left-hand side, you can see our corner reflector. We can actually make that move, and we'll do that a little bit later. Here's the GNU radio flow graph. Let's go ahead and start that. And the FFT comes up, you can see that. So right now we're outputting one continuous frequency, but we can change that to what's called continuous triangle. So here we're ramping the frequency up and then ramping it back down again. And you can see what that looks like on the waterfall plot here. So this is all for a stationary target, but that's not very exciting. So we can make our target move on the target trolley. And you'll notice that as the target gets closer to the antenna, that the beat frequency gets closer to its 100 kilohertz carrier frequency. And as the target moves further away from the antenna, we get further away from that 100 kilohertz frequency. That beat frequency is directly correlated to the distance to target. And here's now the sawtooth. The sawtooth, since it doesn't have the ramp down, you only see the positive deviation in beat frequency there. We'll switch back to continuous triangle mode. But now we'll start increasing the ramp time of that frequency ramp. And you can see the impact that that has on beat frequency. As we make that ramp longer, the beat frequency for the same bandwidth goes down.
Okay, so basically, so we control the external components directly from the flow graph, and this way you can actually play with all the characteristics of the system while you're evaluating it. So there are multiple ways to accomplish that. So that is what we just seen. We had like a Raspberry Pi just as a control bridge. Wired it back to the computer that runs the GNU radio, and we have the digitizer also connected to the same PC. As an alternative, if you have a Raspberry Pi, you can also run GNU radio on the Raspberry Pi, and I call this the OnBased Compute platform, where you just connect the HDMI monitor and USB to that Raspberry Pi. A third, and probably the most interesting alternative, is what I call the all-digital back to the same SoC FPGA. So that basically means your transceiver data, your transceiver control, all the clock control, all the microwave RF front-end control runs back to the same entity. So this enables a single cohesive environment to interface with digitizers, RF and microwave. It has lots of benefits. For example, easier synchronization between your digitizer and your microwave, or a better synchronization of data and control. And we can control all this together from GNU Radio, Matlab, or Python. On kind of this slide, we kind of show that. On the back end, all the components remain actually the same. And on the front end, where we have our compute, we can either use GNU Radio, Python, or Flowgraph exactly in the same manner. And there are different ways to actually integrate that. There's GRIO in GNU Radio. There's the Matlab system object in Python, in Matlab Simulink, and or libio in general for Python. So the presentation is named Kuiper Linux. So what's so special about Kuiper Linux? It's actually just a distribution based on Raspberry, but not only for Raspberry Pi. So it incorporates Linux device drivers for a lot of ADI products, and is kind of created with easy use in mind. So it supports multiple circuit node evaluation board, FMC boards, Raspberry Pi heads, Arduinos, or PMOD connections. And it's kind of out there to just to minimize the barriers to integrate hardware devices into a Linux system. So you don't need to compile the kernel, it's all there. You don't need to install GNU Radio Companion on it. It's all there. There's all Python, libio. It's kind of out of the box. And we also use this for customer evaluation, where they want to have a good out-of-box experience, plug and play, and it all works. So Kuiper solves this by including a lot of host of additional applications, software, and libraries, and utilities. So how do you get that? So there's going to be a imager utility for Windows, Linux, Mac that kind of downloads the latest image from the internet while it actually writes it to the SD card. There's some extra menus to customize the boot partition for a certain carrier, FPGA, FMC add-on card. And this utility is going to be released in the coming weeks. But as an alternative, you can just VW get the image, unzip it, and just dump it on a SD card. And later on, you just move some files around. So I mentioned customizing. While Raspberry just targets Raspberry Pi, this distribution includes lots of bit streams, kernels, device trees for a lot of different popular FPGA carriers from Xilinx, AMD, or Intel, for MPSoC, SoC FPGA, Area 10, Area 5, and so forth. So what is customizing? It's basically configuring the SD card to be used with a specific hardware, and hardware can mean base platform plus attach, and it's basically moving files around so that the first stage bootloader can pick them up. For Raspberry Pi, there's a special thing that's just special to the Raspberry Pi first stage bootloader. There's a file, it's called config.txt, and you can edit that file and kind of instruct the system to load a certain device tree overlay. So what is a device tree and what is an overlay? And at the end of the day, kind of writing device trees is more or less the only thing that you have to do with this distribution if you want to enable certain devices to be present in your system. A device tree is a tree data structure with node that describes physical devices in the system. It's typically used to describe device information that cannot be auto-probed. For example, a USB bus can be auto-probed, PCI bus can be auto-probed, a memory mapped XE bus cannot be auto-probed. It's organized in nodes and in properties. And overlays are kind of a special device tree that allows you to add nodes to a device tree, a running device tree on an active system. So there are various formats of those device trees. So there's one, the textual format, that is human readable, and it's kind of the file that you edit, and you convert that file into a binary file, which is then machine readable using a device tree compiler. And you can use that compiler in both directions. You can also disassemble device tree binary into a source file again. So let's look a little bit how a device tree looks like. On the right side, we see an example. So there are first two directives. Those are for the compiler, and then we have nodes. And we basically want to add a node for our ramping digitizer. So, but we need to create that node somewhere. And you basically create that node under the bus where this device is attached to. In this case, it's a SPI device, so we attach it under a SPI bus node. And in this case, we attach it to SPI bus 0, so we just reference that node, and then we add a node. And in that node, there are a number of kind of required properties. One of them is kind of the compatible property. It's kind of a string, and that string is being matched when the device tree is loaded against a list of available device drivers in your system, and in case those both match, then the kernel instantiates that device using that particular driver. And we are having here a kind of a SPI device, so another important property is the rec property. And in this case, it instructs the SPI subsystem to use chip select 0. So there can be other properties in here, like SPI max frequency, SPI modes, polarity, CPHA bits, and so forth. So in our analog devices Linux kernel tree, which is nothing special, but we have a bunch of extra files in there that are not upstream. It's kind of device tree overlays, for example, we kind of create them just for internal testing and also for customers who just want to test something without actually writing something. And those are located in ARC, ARM, boot, DTS overlay. And once on the SD card image, they are on the first boot partition, which is typically a FAT partition, and you can find those compiled device tree overlays in boot overlays, or from within the root file system of your running Raspberry Pi, those are mounted to boot overlays. There are basically, for Raspberry Pi, there are two kind of methods how you can actually instantiate a certain device tree overlay. One option is to do it at boot time by editing the config.txt file on the boot partition. So you just add a line dt overlay equals kind of the overlay name, excluding the file suffix. Or you can also do it from the command line by typing dt overlay and then the overlay name. You can also remove those overlays if you want. So at this point, we have a kind of a running Linux kernel system that we just added new drivers to it. And now how do we want to use it? Most of the drivers that we do, which are kind of interesting for these RF systems, are so-called I/O drivers. And I/O is a kernel subsystem that is not really just for industrial input-output. It basically covers all non-human interface devices. And that includes ADCs, DACs, transceivers, synthesizers, amplifiers, gyroscope. There's actually a pretty long list. So what are I/O devices? So they are kind of represented as files or directories in a virtual file system called sysfs on your running Linux system under sysbus I/O. And each of these devices do have a structure. A device can have attributes, can have many attributes. A device can have channels. Channels can have attributes. Channels can have events, and also events can have attributes. Devices can also have one or multiple buffers, and buffers can also have attributes. So what are attributes? Attributes describe hardware capabilities, for example, sampling frequency or controlling a certain power mode, power down, for example. You can, on a PLL, you can use PLL locked to check whether the PLL has locked. I/O channels. So channels are a representation of a data channel. Channels always have a direction, can be input or output. Channels do have types, whether it's a voltage, whether it's a temperature, an alternating voltage, whether it's humidity. Basically, there's a long list of different types. Then channel can have index and can also have like modifiers, for example, I and Q. And also channels can have attributes. And in this case, we see frequency as the attribute, but there can also be like phase, hardware gain, scale, offset, draw. And the nice thing about I/O is that those things are kind of standardized, and you can construct physical SI units from it. For example, if you want to know the real voltage on a channel, you basically take the raw attribute, add the offset to it, and multiply it by the scale. And then the convention is that the result is in millivolts. Here's an example how to control a gain amplifier or an attenuator. The difference here is just that the hardware gain is negative. Here in this example, we just write 6 dB into voltage hardware gain, and after we read it, we kind of returns 5.675 because that was the closest possible value that this amplifier could do. Here we have the fast ramping waveform generator that's being used in this FMCW radar system. Again, this device has just one channel, alt voltage 0. That means it's an alternating voltage. And then we have frequency, deviation range, deviation step, deviation time, power down, ramp mode available. And on the right top side, you kind of see where that maps to your waveform. Start frequency, deviation range, which is kind of the bandwidth of that signal, and the deviation time. And these kind of attributes or properties directly map into your radar equation. You can also select different modes for the ramping, sawtooth, or sawtooth burst, continuous triangle, and so forth. And you do that by just writing strings into that attribute. So how do we control this from our GNU radio flow graph? As part of GRIO, there are the IO attribute sync blocks, and these are generic writers for any attributes for IO devices. This includes channel, device buffer, device debug, or even like direct register writes. All the messages must be PMT dictionary, where the key is the attribute and the value is the value that is going to be written. So this block has a number of properties. One is the URI. It can be an IP address. It can be a USB URI. It can be serial. It can be many things. Then we list the device name of that IO device, what kind of attribute type it is. In this case, it's a channel, and it's an output channel, and the channel name is alt voltage 0. Since GNU Radio 3.10, there's a very nice new block. It's called Blockswar to message, and this block will monitor a variable, and when it changes, it generates a message. So before that block, there was also like an IO attribute updater, but that IO attribute updater would just like read a variable, and with a certain rate, it would just hammer it into the device. And sometimes this can have some side effects, for example, some glitches in RF, and you just want to do that if you really change a variable in your system. But kind of the downside with this is that this block has a callback that emits a PMT message pair. And that is not compatible with the IO attribute sync. That's why we kind of, in this example, added kind of a custom Python block of type GR basic block. And this block will convert the PMT message pair into a PMT dictionary. You can see kind of the basic Python code on the right side. This is how the control portion looks like for all the different properties of our frequency ramping generator. We created some Qt GUI widgets, a Qt chooser for the different ramp modes, a toggle button for the power down, and some Qt range widgets for the frequency, ramp rate, and so forth. And for each of those, we have this variable to message block, which connects to our translation block, and then to the IO attribute sync. So some of the conclusions I had was that you don't need to be a Linux expert to use and enable ready-made Linux device drivers. It can actually be quite easy. It's most of the time just like editing a device tree, or when you use Kuiper, you don't need to rebuild your kernel because all the drivers are enabled. GRIO can be used for much more than just controlling a transceiver or digitizer. You can also do some front-end controls with it. And maybe GRIO IO attribute blocks need to be updated to also accept PMT message pairs, or maybe the new PMT messaging that we just heard about will maybe solve this problem also. I don't know. If you're more interested in GRIO and the next generation of libIO, there is going to be a talk, I think it's on Thursday, from Paul. He will talk about libIO design and how it will affect GNU Radio. He will talk about multi-buffer support, async protocol, DMA-buff compatible interface, and a new timestamp API that is also currently discussed. Also, maybe even with the latest version of libIO 0.24, it also supports now hardware monitoring devices. So if you are interested in kind of integrating your CPU temperature or your fan speed into your flow graph to do something differently, you can do that with that. So thanks, everyone. I put in some references, and that's it.
Thanks. I don't see any questions from the internet yet, but I'm somewhat curious. Are there going to be versions of this for x86 and AMD 64 hosts, or is this designed to make embedded use a little simpler, and those of us with bigger computers shouldn't?
So you with libIO, you can run libIO today on your x86. So lots of notebooks to actually use IO for the gyros or for for various other things. And libIO has kind of this remote backend mechanism. So you use libIO on your x86 system, but it can magically connect to a remote backend that runs on an embedded target. And that's being used heavily in all these examples. So you can connect to your FPGA platform, to your Raspberry Pi, and have the IO devices on your x86 system, just like they would be local to your embedded system.
Thanks. Do we have any other questions from the room? No more questions from the internet? Okay, thank you again.